Welcome to Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Sometimes things happen in space science that are somehow simultaneously awesome, make me feel old, and make me feel sad. For instance, on December 19th, 2024, we marked 53 years since humans last walked on the moon. Humans walking on the moon is awesome. I know I was born 1 year after the last moon landing, so that makes me feel old. The fact that it took less than a decade to plan and execute those original moon landings, and it will have taken more than half a century to return to the moon, that makes me feel sad. The thing is, doing extraordinary things takes a vast effort that combines money, people, and infrastructure creation. Each decade, it seems, brings us some new marvel or two of exploration. In the 50s, we went to space. In the 60s, we went to the moon and the inner planets. In the 70s, we launched the Voyager missions to the outer solar system and built our first space station. In the 80s, we had the space shuttle, and we started work on the great observatories, Hubble, Compton, Spitzer, which would launch in the 90s and early 2000s. This constellation of missions was designed to give us full and simultaneous access to the vast majority of the electromagnetic spectrum, stretching from the infrared out to the X-ray. While Compton didn't last long enough to see that vision happen, its successor, Chandra, did. And for a glorious period in the early 2000s, amazing acts of multi-wavelength astronomy were just another day of research. Today, things are even better, with Fermi taking astronomy out into the shortest wavelengths of light, the gamma rays, while JWST has replaced Spitzer with even more sensitive long wavelength infrared observations. And Hubble and Chandra are continuing to just plug along. Here's where that feeling of old part comes in. Hubble launched back in 1990 when I was in high school, and it just turned 35 years old. Here's the happy part. Hubble continues to do remarkable science and is the go-to instrument for folks needing high-resolution images in visible and infrared. But there is sadness. HST was last updated in 2009, and we're not entirely sure how much longer it will last. It's already given us a few scares when its systems threw errors, or, well, the system has flown errors. To be fair, HST was designed for a 15-year mission that included regular refurbishment. 35 years in orbit is kind of miraculous, but it is also forced. While the planned Roman Space Telescope will replace some of HST's capabilities, it isn't a direct replacement. It lacks the UV capabilities, and its instruments are very different. There is no real Hubble replacement planned. And here's the thing. Hubble is just one of a small horde of past their best-by date space missions that are out there collecting data that researchers rely on to study our world, our solar system, and the entire universe. In this week's Closer Look, we're going to look at the Earth-facing missions that are getting dragged down by our atmosphere and will be forcibly retired by physics in the next few years. Again, with no replacements in the works. These missions allow us to do long-term monitoring of our planet, its atmosphere, and the variables that help us understand everything from weather to climate change. We also look at cool new exoplanet discoveries and the beautiful death of a star. All this and more is coming to you right here, right now, on EVSN, a product of CosmoQuest and supported through our Patreon. The universe sometimes likes to mock us. Such is the case with exoplanets. Once upon a time, researchers would sagely say solar systems like Tatooine with twin stars likely don't exist. The thing is, this was based on models that relied on limits created by human minds. And reality is a lot more creative than we are. Over the years, we've found just about every kind of planet in just about every kind of situation. They snuggle with their stars. They run loose through the galaxy. They've been seen orbiting one star in a binary system, and they've been seen orbiting both stars in a binary system in the same disk as the stars. And now we have found a planet, we think, that is orbiting around a pair of brown dwarfs at a right angle to how they are going around one another. And the whole thing is being slowly orbited by yet another star. The inner two stars in the system are similarly sized, tiny brown dwarf stars that are only about 35 times the mass of Jupiter. As researchers watch them going round and round in an eclipsing orbit, it's possible to see their orbits rotate over time. This kind of a motion requires some other mass to be out there exerting a force on the system. The source couldn't be another star, or it would have been seen, so it had to be something smaller and fainter. Other possible sources, like the spins of the stars and their orbits being out of alignment, wouldn't have created the changes that we are currently seeing. They create much smaller changes. Only two possibilities seem to work. Either there is a planet in a perpendicular orbit that is yanking the tiny stars, or there's some kind of a debris disk. Well, the possibility of a debris disk can't be eliminated. The system appears to be old enough for any protoplanetary disks to be done forming, and we'd also expect to see infrared light from such a disk, and we don't. This means a weirdo planet is the system's best explanation. How does a planet get into that kind of an orbit? Well, I look forward to seeing what the theorists come up with. And when their papers come out, we'll bring them to you right here on Escape Velocity Space News. One of the most mystifying planets to many of us are the hot Jupiters. These massive worlds have orbits smaller than Mercury's, and in some cases are so close to their stars that starlight is pushing mass off the planet, or the planet is raising tides on the star. Exactly how you snuggle a planet next to a star and have it stay there is confusing. And now we know not all the planets succeed in getting close without falling in. Back in 2019, a star about 12,000 light years from Earth in a particularly crowded part of the sky was observed by the NEOWISE mission to start shining with a lot more infrared light. Its color literally changed. Then a year later, in 2020, the Zwicky Transient Facility saw a flash of optical light consistent with a planet getting chomped on by its star. It was initially assumed that the reddening we saw was associated with an aging star starting to evolve into a red giant, and that the star was eating its worlds as it expanded in size. This kind of evolution and planet-eating behavior is exactly what we expect of our sun. And researchers were able to get JWST time to look at this system and see what could be learned. With JWST's extra detailed view, they were able to better measure the star's light separate from all of its neighbors' light. And it appears the star isn't actually evolving into a red giant. Instead, it appears that a planet tried to snuggle in toward the star but was disrupted. Its debris field would have been heated by the star, and it's that debris field that's radiating in the infrared. Now, ultimately, whatever was left of that planet plunged in, and the energy released in the process created the flash that the Zwicky Transient Facility detected. Today, a hot disk of gas wraps around the star. This was the first detection of this kind, but with Rubin Observatory gearing up to start monitoring the sky for things that flicker and flare in the night, We can hope that more such flashes will be caught. The JWST observations were part of a multi-telescope, multi-nation program designed to point telescopes at weirdly changing places and to see what is going on. And this target of opportunity plan will allow future sources to also be observed. It's cool to think that we first discovered hot Jupiters in 1995, and just 30 years later, we're starting to catch hot Jupiters falling into their stars. One of the justifications for building the Hubble Space Telescope was to finally get a detailed enough view of the fuzzy blobs we call planetary nebulae that we could finally understand what is going on in these systems. Turns out, for some of the nebula, we actually needed something even better than HST, and that better than is the JWST. First catalogued in 1790 by William Herschel, NGC 1514 is a binary star system surrounded by a glowy blob of stuff. One of the stars is actually a stellar remnant, a hot white dwarf that has shed its atmosphere and stopped undergoing nuclear reactions in its core. Once upon a time, this was the larger of the two stars, but in its death, it transferred a lot of its mass to the system's surroundings. The other star is a bluish giant star that is clearly visible in the center of the nebula. The heat from the two stars heats the lost mass to shine bright in the infrared, where it looks radically different from the spiral graph cloud we see in the optical light. Our first good look came from the WISE Space Telescope, which revealed a pair of rings. This distinctive shape is in part an optical illusion. There's actually a flattened hourglass of material that is pinched in the center by the star's orbital disk. The bands we see are the edges of the bubbles, and this is actually a pretty common shape. WISE's fuzzy blob wasn't entirely satisfying to folks trying to understand the details of stellar death. So JWST took its turn. And wow, just wow. In the new images, we see the warm dust of the hourglass's edges and sides. The WASP waist is hard to see even in this image, but if you follow the white boundaries and look at the curved-in orange dust, you can see it. In the center, the lumpy pink nebula, that's heated oxygen. This system is one that will only last for the blink of an eye on cosmic scales. Over time, the dust and gas and the white dwarf star will cool and fade, and the material will continue to drift away across the millennia. But then, this system will do something kind of awesome. It will form a second nebula as that second star exhales its own atmosphere and evolves into a second white dwarf. And who knows, maybe one day the two white dwarf stars will also merge and explode and create yet a third artistic moment of glory. Our universe loves to change. Up next, we're going to take a closer look at the suite of Earth-observing satellites currently observing our changing world. Stay tuned. There are currently about 20 NASA Earth-observing missions circling our world, either as singular flagship spacecraft or as constellations of small satellites that work together to do their science. These missions collectively observe everything from the chemistry of our atmosphere to the flux of solar radiation on our world to the planet's thermal behavior and changing sea levels. Together, these spacecraft provide continuous monitoring of our evolving world over time. Unfortunately, many of these missions are already working on borrowed time. ACE, Cygnus, Jason 3, Landsat 7 and 8, and SMAP are all beyond their proposed end dates. And Aqua, Aura, Discover, Grace, and Octo 2 are all slated to end in the next year, and not all of them can just keep working with additional funding. And we need to talk about what this means. The trio of missions, Terra, Aqua, and Aura, are environmental science satellites. Terra is a flagship mission of the United States, Japan, and Canada, and it's working to study our world's atmospheric composition, thermal behavior, and changing air, land, and water using a suite of imagers and spectrographs. Launched in 1999, this mission helped us understand how air flights drive cloud formation. It has brought us spectacular images of hurricanes, dust storms, wildfires, and more. Terra is in a sun-synchronous polar orbit, allowing it to get image after image of our world with similar lighting conditions. Located in low Earth orbit, Terra is subject to drag from our Earth's extremely thin atmosphere at that altitude. And as much as we might want to, we can't keep it going forever. Current plans are to deorbit the bus-sized spacecraft sometime later this year or next. And there's nothing planned to replace it. This story also applies, with some plot twists, to Aqua and Aura. Aqua launched in 2002, and its instruments are focused on Earth's water, with systems designed to monitor clouds, atmospheric temperature and humidity, land and sea temperature, and more. Slated for a 5-year mission, it's still going 23 years later. But it has long run out of fuel, and current models suggest drag will deorbit it sometime in 2026. Aura, the third of these sun-synchronous polar orbiters, launched in 2004 and is a collaboration with the European Space Agency. It is focused on our atmosphere and lets us know everything from the status of the ozone hole to the effects of rockets and burning up satellites on the atmosphere. And guess what? It too will likely deorbit in 2026. These missions all caught the attention of the media, with outlets ranging from the New York Times to Politico to Scientific America, all speaking out about the loss to science that this will cause. Of immediate concern, we will be losing the information they capture on how ash from volcanoes, smoke from fires, dust, and pollution all move through our atmosphere and affect the air quality and weather patterns around the world. Longer term, they monitor the no longer healing ozone hole. While we can hope to launch missions to collect data in the future, without overlapping data from the current and future instruments, figuring out how to calibrate their data sets for long-term studies will be next to impossible. As researchers, we're kind of expected to do the next to impossible every day. This is how we end up with still working 25-year-old spacecraft that were originally launched on 5-year missions. But it would be a whole lot easier to understand our world if we had continuity between Earth-observing missions. And what is concerning to me and many others is Terra, Aqua, and Aura were major missions from the golden era of NASA getting back into the science game. These Earth observers were worked on at the same time that NASA was building the great observatories and follow-up missions like Chandra, Fermi, and Webb. There is nothing currently planned to replace any of these flagship missions of the 80s, 90s, and early 2000s. And while I love those eras of music, I like my space missions a bit more modern. NASA currently shows 3 smaller missions in the planning stages, and none of them will replace these Earth-observing capabilities. But Terra, Aqua, and Aura are just 3 of the 9 that are nearing end of life. The Deep Space Climate Observatory, or DSCOVR, is another Earth observer. Launched in 2015 on a 5-year mission, it is still going strong 10 years in. Placed at the L1 Lagrange point between the Earth and the Sun, its data aids in weather forecasting and space weather prediction. That's the stuff that tells us when aurora may be visible. We don't have to worry about it falling out of orbit, and it should be able to carry on its mission as long as its computers work, which could mean decades. But are we going to keep relying on decades-old spacecraft when most of us don't trust even 5-year-old phones? I could keep going, could keep telling you about GRACE and Octo 2 and Landsat 7 and 8 and all their aged missions that are still doing their jobs because engineers building for NASA like to build things that last. And I'm grateful that they are still going. I am grateful that our science for now will keep going because of that over-engineering. But we are in a situation where it takes years to decades to develop, build, and launch satellites. And we don't have replacements currently being planned. Instead, as we discussed last week, we have massive slashes coming to NASA, and the possibility that nearly complete space missions, like the Roman Space Telescope, will be canceled. As long as they don't take the missions apart, canceled doesn't have to mean forever. Discover was actually canceled under the second Bush administration and pulled out of storage and refurbished and launched in the Obama administration. But can we, as a planet, afford a gap in data right now? Each year, the ocean temperatures are driving more rapidly growing hurricanes and more powerful storms. Changes in rain patterns are driving fires with continent-covering smoke. We are seeing dust storms from Africa laying sand over Europe. And it is the Earth-observing missions that allow us to see in detail what is happening. We currently use a multi-pronged, okay, I'm going to go back a couple sentences. And it is the Earth-observing missions that allow us to see in detail what is happening. We are currently using a multi-pronged data collection process. Discover, out at L1, can image the sunlit side of our planet over and over, giving us a picture of our world. From their low Earth orbits, Terra, Aqua, and Aura are getting detailed images of stripes of our planet with repeat images being taken roughly every couple weeks. And with airplanes, drones, and ground stations, we get the most detailed measurements covering the smallest areas, but covering them moment by moment. All this data is needed in our weather models to produce the more or less accurate storm predictions we have today. As someone living in Tornado Alley, I appreciate the heads up on when I need to be ready to hide in the basement. And when it is alternatively fine to go out on a 4-hour bike ride. It turns out that blue skies at 9 a.m. can quickly be erased by severe weather, and these kinds of forecasts are necessary not just for safety, but also for the economy, as they are used to guide planting, shipping, air travel, and so much more. And we are going to start losing this data, either later this year or next year. This will be one more thing negatively impacting our economy and our safety that we need to be aware of. Folks, I don't know what happened 20 to 30 years ago politically that led to so much money going to science missions. It was a drop in the bucket compared to the 60s, but it was enough to set us up for the science-guided world we live on. In this age where tourist flights above the atmosphere are possible, it feels like getting more science missions shouldn't be so impossible. But right now, as we watch more rockets going up than at any point in history, we aren't launching all that many science missions. This is our reality. There's no easy way to summarize this segment. We are nearing the end of an era, and soon we will see missions failing, from Hubble looking outwards to Terra and company looking down. And our ability to keep up our current pace of science will falter. After a break, we'll be back to look at this week's Tales from the Launch Pad without all that much science. Stay tuned. Next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launch Pad. Hey, Eric.
Hi, Pamela. Today the part of Eric will be played by me, Allie. Usually I'm behind the scenes producing and editing EVSN, but today I'm stepping in front of the camera so Eric can get some much needed rest. There were too many launches to cover every single one, so we're bringing you the highlights. Let's get into it. On April 21st, SpaceX launched its 32nd Commercial Resupply Services mission from Launch Complex 39A at NASA's Kennedy Space Center on a Falcon 9 rocket. Let's watch the launch.
And here we go. In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition and liftoff. Liftoff of CRS-32. 6,700 pounds of science supplies at the International Space Station. Falcon 9 has cleared the tower.
CRS-32 delivered around 3,000 kilos of cargo, including crew supplies, science investigations, spacewalk equipment, vehicle hardware, and computer resources, to the International Space Station in a Dragon spacecraft. Dragon will spend about 1 month on the space station before undocking and splashing down off the coast of California. Also on April 21st, SpaceX launched another bandwagon rideshare mission from Slick 40 at Cape Canaveral Space Force Station, also on a Falcon 9 rocket. Let's watch that launch.
5, 4, 3, 2, 1. Ignition. Engines full power and liftoff. Go Falcon, go Bandwagon 3.
Stage 1 propulsion is nominal.
Vehicles pitching downrange.
Bandwagon 3 carried satellites for multiple commercial and government customers to a mid-inclination orbit. And now for the part of the segment where I trip over pronouncing Chinese names. Enjoy. On April 24th, China launched the Shenzhou 20 mission from Jiuquan Satellite Launch Center on board a Long March 2F rocket. Let's watch the launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1,点火。
起飞，70，摇拐时，摇拐分31秒，441毫秒，70，摇拐时，摇拐分31秒，441毫秒。
9前程序转弯，
程序转弯。
9前光学跟踪正常。 青山 USB 雷达跟踪正常，遥测信号正常。
双城光学雷达跟踪正常。
东风光学 USB 雷达跟踪正常，遥测信号。
Shenzhou 20 carried 3 taikonauts to the Tiangong space station. This is the 15th crewed Chinese spaceflight and 20th flight overall of the Shenzhou program. On April 27th, the Chinese Aerospace Science and Technology Corporation launched a second-generation Tianlian satellite from Xishang Satellite Launch Center on a Long March 3B. Let's watch the launch. This is the 5th satellite added to China's geostationary Tianlian data tracking and relay communications satellite series. On April 28th, United Launch Alliance launched Amazon's Project Kuiper from Slick 41 at Cape Canaveral Space Force Station on an Atlas V rocket. Let's watch the launch.
5, 4, 3, we have ignition, 2, 1.
Ignition and full thrust. 5 good SRBs.
And liftoff of the United Launch Alliance Atlas V rocket, carrying satellites for Amazon's Project Kuiper internet constellation, marking the start of a new chapter in low Earth orbit satellite connectivity.
View is now on closed loop control, engaging first throttle segments. And we've completed our pitch program.
Engine operating parameters continue to look good. And we've successfully completed our roll program. Hydraulics continue to operate nominally. Mach 1, Atlas V is now supersonic. Body rates continue to look good. Engine continues to operate as expected. Throttling back up.
You are hearing Sarah Bailey Glasgow providing launch vehicle ascent data.
We are now 7 miles in altitude, moving at 1,700 miles an hour. Now passing 1 minute into flight. Vehicle continues to pass through the center of the rain track as expected. SRBs continue to operate nominally. Throttling down, engine continues to burn as expected.
Project Kuiper is Amazon's planned low Earth orbit satellite broadband network. On April 29th, the European Space Agency launched its biomass mission from Europe Spaceport in French Guiana on a Vega C rocket. Let's watch that launch.
5, 4, 3, 2, 1, top, allumage P120, décollage. Propulseur nominal, début du basculement. Propulseur nominal. Pilotage calme. Trajectoire nominale.
Per ESA, biomass will use novel P-band synthetic aperture radar to essentially weigh and categorize Earth's forests every 9 months for the next 5 to 6 years. This will provide much-needed information on the role forests play in the planet's carbon cycle. Also on April 29th, Firefly Aerospace launched the Message in a Booster mission from Vandenberg Space Force Base in California on its Alpha rocket. Message in a Booster attempted to carry a Lockheed Martin LM-400 satellite bus into polar orbit, but despite the upper stage's best efforts, the satellite never made it into a viable orbit after the upper stage engine bell was destroyed during booster separation, making this a launch failure. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 59 launches, China 24 launches, New Zealand 5, Russia 3, French Guiana 2, Kazakhstan 2, India 1, Japan 1, and Norway 1. Of these 98 launches, there have been 5 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I want to bring you a story that somehow explains the culture of science in ways few stories can. You've all heard of the space race to get to the moon in the 60s, and people talk about there being a modern space race to return to the moon. But there are a whole lot of other races that go on in academia, and my favorite genre of competition is which culture did what first. From recording supernova to carving eclipses into stone, archaeoastronomers are constantly looking for scientific measurements made by our most distant ancestors. And right now we're seeing an isn't it debate over Chinese star chart's possible origins in 355 BCE. Called the Shi Catalog, this star chart can be interpreted in 2 different ways. In one scenario, the stars' positions were measured in 2 batches, with one hemisphere measured in 355 BC and the other in 125 BCE, making the older portion of the catalog significantly older than the catalog of Hipparchus. This would give the Chinese culture bragging rights. This dating comes from using software to see when the stars were located where they appear in the map. Because our planet has a slight wobble, stars ever so slowly drift through the sky, and measurements relative to the Earth's rotational axis allow us to reverse engineer the dates of the measurements. When you see stars in one map matching 2 different sets of dates, you do have to ask, could something else explain what we're seeing? And this brings us to scenario number 2. If the instrument used to measure the stars' positions just happened to be misaligned by about 1 degree, then the data is consistent with all the stars being observed at the same time around 103 BCE. This would make the catalog slightly younger than the Hipparchus catalog, but like 30 years younger, which isn't a lot compared to the difference between those two catalogs and the Babylonian records, which are from the 8th century BCE. So really, they're competing for second place, and in the grand march of time, they most likely are tied. But people are still going to argue, and I will be amused. And that's it for now. Good night, everyone. And remember, go look up.